Look at a low, wind-scoured ridge of gravel and granite 300 kilometers northeast of Yellowknife in the Northwest Territories. An expanse of dwarf birch, gray lichen, and scattered glacial boulders stepping down into a shallow, ice-carved lake. For decades, pilot logs and survey maps recorded this landscape as empty tundra, a barren stretch of the Slave Geological Province where winter lasts 8 months and nothing of commercial value could sit in the ground. But beneath these exact gravels lay one of the densest concentrations of gem-quality diamonds ever formed in the Earth's mantle. What is remarkable is not simply that the diamonds existed, but that geologists from the world's most powerful mining conglomerates had surveyed the Canadian Shield for half a century and concluded it held no economic kimberlite pipes whatsoever. How did two independent geologists working with hand-sampling pans and a single leased helicopter outsmart global mining houses to trigger the largest land staking rush in North American history? And what remains when the corporations that followed them move on? To understand the scale of the oversight, one has to look at what the global mining industry believed about Canada before 1991. For over a century, commercial diamond production was dominated by southern Africa, Siberia, and Western Australia. The conventional geological consensus held that while ancient continental cratons, the stable rock cores of continents known as shields, were necessary host environments, the North American craton was either too deeply eroded or lacked the mantle chemistry required to preserve diamond-bearing kimberlites. In the 1960s, exploration teams from international mining houses conducted brief reconnaissance trips across parts of northern Canada, found little of interest, and withdrew. The assumption that the country held no economic diamond deposits was firmly entrenched, published in standard textbooks, and treated as settled fact. That assumption was entirely reasonable at the time. Canada had no history of diamond mining, and kimberlite pipes are notoriously difficult to find. They are geologically tiny targets, often measuring less than 300 meters across. In the Slave Geological Province, millions of years of weathering followed by heavy glaciation had scoured out the soft kimberlite rock faster than the surrounding granite, creating natural depressions. When the continental ice sheets retreated roughly 10,000 years ago, those depressions filled with water. The deposits were not sitting exposed as hills. They were hidden beneath shallow tundra lakes, buried under meters of glacial mud and gravel. The first crack in the consensus did not come from a multi-million-dollar corporate exploration budget, but from a painstaking reconstruction of glacial physics. In the late 1970s, field geologists Charles Fipke and Stuart Blusen began testing a technique that would take more than a decade to bear fruit. They understood that when Pleistocene ice sheets scraped across the shield, they ground down any exposed rock formations and dragged the debris southwestward, depositing long dispersal trains of sand, gravel, and heavy minerals across hundreds of kilometers. If a diamondiferous pipe existed somewhere on the barrens, it would leave a microscopic trail in the glacial till, specifically heavy indicator minerals such as chrome pyrope garnets, picroilmenites, and chrome spins. The work was slow and physically demanding. Sampling meant landing a float plane or helicopter on remote lakes, digging through surface till, and panning heavy mineral concentrates by hand in freezing water. Working through their small company, Diamet Minerals, Fipke and Blusen spent the 1980s quietly gathering thousands of till samples across British Columbia, the Yukon, and the Northwest Territories. They brought the samples back to laboratory microprobes to analyze their exact chemical composition. They were looking specifically for subcalcic G10 garnets, which form under extreme pressures more than 150 kilometers below the surface, the exact environmental window where carbon crystallizes into diamond. For years, as the indicator trail slowly led them northeastward against the direction of ancient ice flow, they published no papers, raised no public alarms, and kept their operational footprint down to a minimum. By 1990, the mineral chemistry pointed directly to the barren tundra surrounding Lac de Gras, a large lake sitting 300 kilometers northeast of Yellowknife. Working in near-total secrecy, they began quietly staking mineral claims over the surrounding terrain before any major competitor realized what the indicator trail meant. The rock hosting these diamonds is roughly 50 to 55 million years old, but the diamonds themselves are far older. formed deep within the Earth's mantle between 1.5 and 3 billion years ago, at temperatures exceeding 1100 degrees Celsius and pressures above 45,000 atmospheres. They sat locked in stable continental roots until violent volcanic eruptions forced them upward. These were not slow lava flows, but supersonic magma conduits known as kimberlite pipes, rising from depths of over 150 kilometers at speeds reaching several hundred meters per second. The gas-rich kimberlite magma blasted through the overlying crust, punching narrow, carrot-shaped funnels to the surface. As the magma cooled, it trapped the diamonds inside a dense matrix of olivine, pyroxene, and serpentine. Over the tens of millions of years that followed, the surface expression of these volcanoes weathered away. What remained in the Slave Geological Province was a basement of Archean granite, pierced by isolated, soft kimberlite columns. Then came the ice. During the last glacial maximum, the Laurentide ice sheet, spanning up to 3 kilometers in thickness, slid across the Canadian Shield. The ice scraped away the top of each kimberlite pipe, crushing millions of carats of diamond-bearing rock into fine debris. Because kimberlite is softer than granite, the ice carved out hollows where the pipes hit the surface. As the ice sheet melted roughly 10,000 years ago, it dumped the crushed debris in long, linear gravel trails known as eskers and till plains extending southwest across the tundra. The water filled the carved hollows, creating the quiet, featureless lakes that line the region today. Indigenous peoples, including the Twacho, Yellowknives Dene, and Lutzelk'e Dene, traversed and hunted across these lands for thousands of years, following caribou migration corridors along those very eskers. The official geological mapping of the North, however, lagged far behind. When field officers from the Geological Survey of Canada conducted regional surveys in the middle of the 20th century, their focus was primarily on gold, base metals, and uranium. Small tundra lakes were recorded simply as water bodies without further investigation. In 1985, Fipke and Bluesen partnered with Hugo de Met, a South African geologist working for Superior Oil, who possessed extensive experience in kimberlite mineralogy. When Mobil acquired Superior Oil, management dismissed the Canadian Diamond Exploration Program as an expensive long shot and cancelled funding. De Met subsequently moved to BHP, one of the world's largest mining houses, and persuaded them to back the search around Lac de Gras. In September 1991, drilling equipment brought to Point Lake, a small body of water near Lac de Gras, bored through 80 meters of glacial drift and water before striking fresh kimberlite core. Subsequent lab analyses revealed a diamond concentration that surpassed almost every known commercial deposit in southern Africa. Word of the discovery leaked in late November 1991. What followed was the largest land rush in Canadian history. Over the next 3 years, prospectors, junior mining firms, and multinational corporations staked mineral claims covering more than 20 million hectares of the Northwest Territories, an area larger than the province of New Brunswick. Planes and helicopters saturated the skies above Yellowknife, flying endless circuits to drop staking crews and wooden boundary posts across thousands of square kilometers of frozen tundra. Yet, drilling a high-grade core sample beneath a frozen Arctic lake was only the beginning. The fundamental question confronting BHP and Diamat was whether a commercial diamond mine could actually be built and operated profitably in an extreme subarctic wilderness with no roads, no power grid, and no surrounding industrial infrastructure. How do you convert a submerged volcanic pipe in the middle of the barrens into a functioning industrial facility? And what engineered proof was needed to convince global financial markets that Canadian diamonds were real? The transition from a single promising drill core to verified economic proof required an overhaul of how geophysical surveys were conducted over northern shield terrain. Standard regional aeromagnetic maps, flown by government agencies in the 1950s and 60s at flight line spacings of several kilometers, were far too coarse to resolve small kimberlite bodies. A kimberlite pipe 50 to 200 meters in diameter simply disappeared between those flight lines. To locate additional pipes buried beneath lake water and glacial drift, exploration companies introduced high-resolution airborne geophysical surveys. Low-flying aircraft fitted with cesium vapor magnetometers and frequency domain electromagnetic systems flew grid lines spaced as close as 50 to 100 meters apart. Kimberlite contains magnetite and clay-rich alteration minerals, creating distinct, localized magnetic and electrical resistivity anomalies. On geophysical profile maps, these targets appeared as small circular magnetic lows or highs, flanked by sharp resistivity drops, standing out against the uniform, resistant granite bedrock. Once an airborne anomaly was flagged, ground teams used reflection seismics and ground-penetrating radar across the frozen lake ice in winter to map the exact contact boundaries between lake sediment, glacial till, and the underlying pipe structure. Core drilling rigs mounted on ice pads then bored down through the lake ice to retrieve continuous rock samples. Yet core samples alone cannot determine whether a pipe can support a commercial mine. Kimberlite geology is highly variable. A single pipe can contain multiple intrusive phases with wildly different diamond grades. To get definitive proof, engineers had to extract thousands of tons of raw rock without building a full-scale mine first. In 1993 and 1994, BHP executed a bulk sampling program at what would become the Akati Diamond Mine site, located near Lac de Gras. They sank an underground exploration shaft into the Panda kimberlite pipe, driving horizontal drifts through the frozen rock to haul out a bulk sample of over 20,000 tons of kimberlite. That bulk sample was processed on-site through a specialized dense media separation plant. The extracted diamonds were categorized, sized, and shipped under heavy security to valuation experts in London and Antwerp. The appraisal confirmed that the Akati pipes held high concentrations of gem-quality stones valued at over $100 per carat, far above the global industry average at the time. By 1996, the environmental assessment process led by federal authorities and northern communities culminated in approval for construction. The scientific proof was complete. The Canadian Shield held world-class diamond reserves. But proving the geology in a laboratory was one thing. Building, operating, and ultimately decommissioning an industrial megaproject on frozen tundra hundreds of kilometers from the nearest permanent highway presented an entirely new set of physical constraints. How does an operation of this scale survive 30 years in one of the most uncompromising environments on Earth? And what happens when the ice that makes it possible begins to thaw? The opening of Akati in 1998, followed by Diavik in 2003 and Gahcho Kué in 2016, transformed the economy of the Northwest Territories. Within a decade, Canada rose from producing 0 carats to becoming the world's third largest diamond producer by value, trailing only Botswana and Russia. At their peak, diamond operations accounted for over half of the Northwest Territories' gross domestic product and provided thousands of direct jobs, creating unprecedented employment and contracting opportunities for local First Nations communities. Yet every ton of diamond ore extracted required massive infrastructure engineered for an environment undergoing rapid thermal change. To reach the submerged kimberlite pipes beneath lakes like Lac de Gras, mining companies had to construct large perimeter dikes directly through Arctic waters, pump out hundreds of millions of liters of lake water, and freeze the underlying foundations into permafrost using thermosiphon tubes. The logistical lifeline for all of these mines is the Tibet to Contwoito Winter Road, a 400-kilometer ice road built fresh each January across 85% frozen lake surfaces. Over an 8 to 10 week window, heavy transport trucks haul fuel, explosives, reagents, and heavy machinery to the sites. Operating this corridor requires precise ice engineering, with ground-penetrating radar towed behind light vehicles to continuously measure ice thickness before heavy loads are permitted to cross. That supply line is now under increasing environmental strain. Shorter winters and higher average temperatures have made the ice road season unpredictable. In 2006, an unusually warm winter forced the closure of the ice road weeks ahead of schedule, requiring operator BHP to airlift millions of liters of diesel fuel to Akati at extreme expense. Natural Resources Canada models indicate that winter operating windows across the subarctic will continue to shorten over coming decades. Simultaneously, the active life cycle of the original mines is nearing its end. Akati and Diavik are both facing planned closures or major scaling back of operations over the coming years, as economic open pit and underground reserves are exhausted. Closing a diamond mine in permafrost terrain carries complex environmental responsibilities. Mine reclamation plans filed with the Wekajee Land and Water Board outline the physical scale of closure. Pit walls must be flooded slowly to restore natural lake levels without disturbing surrounding water chemistry. Waste rock piles, massive man-made hills containing hundreds of millions of tons of granite, must be permanently capped and monitored to ensure permafrost reestablishes itself inside the rock mass, preventing acid rock drainage or metal leaching into surrounding watersheds. The total liability for reclamation across these sites runs into billions of dollars, backed by financial security bonds held by the territorial government. The economic footprint is shifting rapidly as well. As processing plants quiet down and workforce requirements drop, northern communities face the loss of their largest private sector revenue source. What remains on the tundra is a fundamental shift in geography, engineered rock landforms and flooded pit lakes that will mark the landscape for centuries. How does a region defined by an extraordinary 30-year boom prepare for the quiet that follows? And what does the story of Canada's diamond rush reveal about how we read the map? The story of the Slave Geological Province is not merely the story of a lucrative mineral discovery. It is a lesson in how institutional assumptions blind us to what sits directly beneath our feet. For nearly half a century, international geological consensus dictated that northern Canada could not harbor major diamond deposits simply because no one had yet proven that it did. The obstacle was never a lack of physical evidence in the ground. The indicator mineral trails stretched for hundreds of kilometers across the barrens, waiting to be read. What kept the deposit hidden for so long was the rigid assumption that a landform lacking an obvious surface expression must be geologically featureless. Even now, the geological inventory of the Canadian Shield remains unfinished. Hundreds of kimberlite pipes across the Northwest Territories and Nunavut have been identified by airborne geophysics but remain untested by diamond drilling. In remote corners of the Slave and Churchill geological provinces, glacial cover still conceals structures whose mantle chemistry has never been microprobed. As permafrost degrades and ice cover recedes, the physical baselines that geologists use to map the North are shifting in real time. The official map presents a landscape of settled contours, surveyed boundaries, and quiet tundra lakes. The ground beneath it tells a far more dynamic story, one of ancient mantle plumes, continental collisions, and hidden structures that defy decades of scientific precedent. Which landscape in your own province or territory has always seemed completely ordinary on the surface, only to hold a history that surprised you when you looked closer? Tell us in the comments below and subscribe for more deep geographical investigation.